Hi everyone, today we will be answering the following question: what is cancer and is it actually curable? I'm Chio. I'll keep our investigation focused on what that question really means. We will follow one normal cell towards cancer and watch treatments exploit particular weaknesses. We will also ask why elephants and mole rats resist tumors unusually well. Then we will return to the word curable with enough evidence to use it properly.
I'm Yuna. I'll help us make sense of the risks, estimates, and uncertainty. The latest World Health Organization assessment describes about 20.6 million new cancer cases in a year. It also estimates close to 10 million cancer deaths. That is roughly 26,000 deaths daily. It is a modeled global estimate, not a live counter. A large number tells us the scale of the problem, not what will happen to one person.
And I'm Sora, here to explore the living systems and biological mechanisms behind the answer. More than 100 types of cancer are recognized, classified by organ, originating cell, microscopic appearance, and molecular alterations. Breast cancer, for example, includes hormone receptor positive, HER2 positive, and triple negative diseases with different treatment options. Asking for one cancer cure is like asking for one repair manual for every machine in a city.
Incidence means new diagnoses during a defined period. Mortality means deaths attributed to a disease during that period. Lung cancer led global incidence and cancer mortality in 2024. It caused about 2.6 million diagnoses and 1.86 million deaths. Breast cancer had about 2.4 million diagnoses, but fewer deaths than lung cancer. Common does not mean equally lethal. Screening, age, biology, treatment access, and the time people live after diagnosis all change the relationship.
Our root begins in an organized tissue because cancer only makes sense against the rules of normal life. We will then examine mutation, selection, invasion, diagnosis, treatment, resistance, and recurrence. Halfway through, comparative oncology will let nature challenge our assumptions about size, lifespan, and cancer risk. This is general education, so personal symptoms, screening, and treatment still belong with a qualified clinical team.
Picture the lining of your colon folded into millions of tiny test tube-shaped glands called crypts. Stem cells near the bottom divide, the descendants move upwards, specialize, perform their jobs, and are eventually shed. The entire lining renews rapidly without normally turning into a heap of competing tissue. That ordinary achievement requires growth signals, positional instructions, repair systems, and reliable ways to stop. A proto-oncogene is a normal gene that can encourage growth when the tissue genuinely needs it. A tumor suppressor gene can pause division, organize repair, or order a dangerously damaged cell to die. DNA repair proteins proofread or mend different kinds of molecular damage. Cancer becomes possible when descendants acquire combinations that press the accelerator, weaken the brakes, and corrupt the workshop. In many colorectal cancers, an early event disables a tumor suppressor called APC. Healthy APC helps control a growth messenger called beta-catenin. Losing APC can make a crypt cell behave as though renewal is always switched on. Its descendants may form a small adenomatous polyp, which is an abnormal growth rather than an inevitable cancer. Most polyps do not complete the journey. Removing selected polyps is precisely why screening can prevent some colorectal cancers. A later clone may acquire an activating change in KRAS, giving growth another shout. Further alterations in growth-suppressing pathways and P53 can help selected cells survive damage. They may then invade and progress from adenoma to carcinoma. The famous APC to KRAS to P53 sequence is a teaching model, not a compulsory molecular timetable. Real colorectal tumors take multiple routes, sometimes through mismatch repair failure and microsatellite instability instead.
This example also separates three words that are often muddled. A neoplasm is new abnormal growth. A benign tumor does not invade and metastasize like a malignant tumor. Cancer refers to malignant disease. A benign brain tumor can still be dangerous because the skull leaves little spare room. Behavior and location matter more than whether the word tumor sounds frightening.
Oncogenes and tumor suppressors fail in different ways. One overactive copy of a growth-driving oncogene can matter. A jammed accelerator still matters even when the second pedal works. A tumor suppressor often loses function after both available copies or the pathway around them are disabled. The analogy is imperfect, but it explains why activating and inactivating mutations are not biologically interchangeable.
Mismatch repair is the spell-checking system that corrects certain errors made while DNA is copied. In Lynch syndrome, a person inherits a damaging variant in one mismatch repair gene. A colon cell therefore begins one protective step closer to failure. If the remaining working copy is lost, repetitive DNA regions accumulate errors, producing microsatellite instability. That molecular signature can help identify inherited risk and can also influence treatment. A cancer cell can change gene use without changing every DNA letter. Chemical marks on DNA and its packaging can silence a repair gene. They can also unlock a developmental program that adult tissue normally keeps quiet. This is called epigenetic alteration, and it can cooperate with mutations rather than replace them. The genome is not merely corrupted text. The system deciding which pages to read can also be mismanaged. Ultraviolet light often leaves a recognizable DNA pattern in skin cancers. Tobacco smoke leaves characteristic mutational signatures in exposed tissues. Persistent human papillomavirus can produce proteins that interfere with p53 and the retinoblastoma pathway. Ordinary cell division also creates occasional copying errors even without an obvious external exposure. These routes alter probability, and none gives us permission to blame an individual patient.
Every healthy adult carries mosaics of cells with acquired mutations, especially in tissues that divide frequently. Most altered cells disappear, remain harmless, or lack the extra capabilities needed to form malignant disease. Cancer usually requires several cooperating changes plus a tissue environment in which the clone can expand. Mutation is necessary to many cancers, but mutation by itself is not a diagnosis.
Up to about 10% of cancers may involve inherited cancer predisposing changes. Inheriting such a variant changes the starting odds, not the ending of the story. A person may never develop cancer, while someone without a recognized inherited syndrome still can. Family history, age at diagnosis, and the cancer pattern can guide referral. They help determine whether specialist genetic assessment may be useful.
Risk is often distributed across inherited susceptibility, exposure agent, and stochastic events during cell division. That mixture is why two people with similar lives can have different outcomes. Prevention can reduce risk substantially without eliminating it. Illness does not prove moral or practical failure. Biology has probabilities, not a celestial point system.
Suppose one altered colon cell produces 1 million descendants. They begin as relatives, but further genetic and epigenetic differences appear while the population expands. Low oxygen, immune attack, and limited nutrients favor some variants over others. Variation, inheritance, and differential survival mean that evolution is now occurring inside the tissue.
A biopsy samples real tissue, but it cannot place every cell from every tumor region under the microscope. One area may contain a drug-sensitive clone, while another contains a rarer resistant clone. Metastases can also continue evolving after they leave the original site. This heterogeneity explains why a precise biopsy can still be an incomplete map of a changing disease.
Malignant cells do not build a tumor alone. They recruit blood vessels and alter fibroblasts. They also signal with immune cells and remodel the protein mesh around the tissue. A dense or poorly perfused region may receive less drug, while local signals may help cells survive. The tumor is therefore an evolving ecosystem whose malignant inhabitants can modify their own habitat.
Treatment kills susceptible cells, which is its purpose, but that success changes the population left behind. If one cell already carries a resistance mechanism, removing its competitors can let its descendants dominate. Resistance can also appear later through mutation, altered gene use, or protection from the microenvironment. The logic resembles antibiotic resistance, although cancer cells are the person's own evolving cells rather than infectious bacteria.
Chronic myeloid leukemia offers an unusually clear example. Most cases contain a rearrangement joining BCR-ABL1. It creates an always active tyrosine kinase that drives abnormal blood cell production. Imatinib was designed to fit the kinase and inhibit its signal. Here, a molecular lesion leads directly to a target, a drug, and a measurable marker in blood.
Before tyrosine kinase inhibitors, chronic myeloid leukemia could progress to a rapidly fatal blast phase unless transplantation succeeded. Current inhibitors have transformed chronic phase disease. Major studies summarized by the National Cancer Institute report 10-year overall survival above 90%. Doctors can measure BCR-ABL1 transcripts. The result shows how deeply the clone has responded. This is not one pill curing all cancer. It is one well-defined dependency being exploited in one disease.
Some leukemia cells alter the kinase so a drug binds poorly. The T315I substitution became a classic example. Researchers responded with inhibitors designed for different binding sites or resistant forms of the protein. The disease teaches both sides of precision oncology. A target can be spectacularly useful, and evolution can still move it. Monitoring matters because the molecular population can change before symptoms make that change obvious.
The chronic myeloid leukemia story gives us a disciplined way to ask about any treatment. What feature is essential to this cancer? Which intervention exploits it? How will response be measured? How might resistance arise? If those 4 questions cannot be answered, the word targeted may be doing more marketing than science. We will use the same framework again when we reach breast and testicular cancer. Now, for a puzzle that initially sounds absurd, an elephant has vastly more cells than a mouse and lives far longer. It therefore has many more opportunities for a cell lineage to go wrong. If every mammalian cell carried mouse-like defenses, a mature elephant ought to be an ambulant collection of tumors. It is not, and that mismatch between simple expectation and observation is called Peto's paradox.
Peto's paradox does not mean large individuals can never have greater risk, nor does every large species outperform every small species. It asks why cancer across species does not rise as steeply as cell number and lifespan predict. Recent data sets disagree about the exact statistical relationship once gestation, mutation rate, and sampling are considered. The robust conclusion is that evolution has altered cancer suppression differently in different lineages.
The tempting claim is that certain animals never develop cancer and are, for all practical purposes, immune. No animal species has met the evidence required for that sentence. Imagine researchers observed 0 cancers among 300 independent animals. The statistical rule of 3 still puts the approximate upper 95% confidence limit near 1%. 0 observations can support very strong resistance, but they cannot prove biological impossibility.
A species may still be functionally cancer-resistant. Its tumors may be too rare or slow to contribute much to normal mortality. A 2025 survey reported neoplasia below 1.3% in common porpoises. The figures were below 1.6% in Rodrigues fruit bats and 0.4% in black-footed penguins. Such estimates reflect defenses, lifespan, and cell division rate. Competing deaths and the frequency of complete necropsies also matter. Immune suggests an absolute barrier. Resistant describes what the evidence can actually measure. One influential necropsy analysis estimated elephant cancer mortality at about 4.8%. That was lower than expected for such a large, long-lived mammal. The comparison was based on historical animal records rather than a perfect population registry. Even so, elephant cells respond to DNA damage differently from human cells in laboratory tests. Instead of tolerating questionable damage, they are unusually willing to trigger programmed cell death. And humans normally have one TP53 gene locus with 2 alleles. African elephants have at least 20 TP53 copies, including retrogenes. P53 detects cellular stress and can pause division, organize repair, or trigger death. After radiation, elephant lymphocytes in the study underwent apoptosis at roughly twice the rate of healthy human lymphocytes. Extra alarms appear to make damaged elephant cells easier to sacrifice before they become dangerous.
Elephants also revived a once disabled copy of a gene called LIF6. When P53 detects damage, it can activate LIF6. The resulting protein moves to mitochondria and helps initiate apoptosis. Researchers nicknamed it a zombie gene because the pseudogene regained a lethal cellular function. The memorable name is delightful, but the mechanism is specific. Damaged cells are pushed more readily towards self-destruction.
Simply giving people more p53 activity would not be an obviously safe anti-cancer upgrade. Cell death protects against tumors, but excessive cell loss could damage organs, impair healing, or accelerate degenerative disease. Elephants evolved an entire regulatory system around these genes over millions of years. Translation means activating a useful pathway in the right cell. It must also act at the right strength and for the right duration.
The naked mole rat approaches the problem differently. This mouse-sized rodent can live beyond 30 years, whereas a laboratory mouse may live only a few years. Its tissues contain abundant hyaluronan, a long sugar polymer that helps organize the space around cells. The naked mole rat version reaches an exceptionally high molecular mass and makes crowded cells stop dividing unusually early. Researchers did more than notice sticky material and invent a story. They reduced naked mole rat hyaluronan production or increased the enzyme that breaks it down. Cells that had resisted experimental transformation then became susceptible and formed tumors when transplanted into mice. Removing the proposed protection changed the outcome, which is much stronger evidence than a correlation alone.
Early reports claimed cancer had never been observed in naked mole rats. Better surveillance disproved that claim. In 2016, pathologists documented an adenocarcinoma in a 22-year-old male. Another animal of about 20 had a neuroendocrine carcinoma. Two cases do not erase the species' remarkable resistance. They do erase the word never.
In 2023, researchers engineered mice to express the naked mole rat HAS2 enzyme. The mice produced more high molecular mass hyaluronan. Those mice showed fewer spontaneous and chemically induced tumors, less inflammation, and longer life than controls. That is an exciting cross-species transfer in an animal experiment. It is still several scientific bridges away from a safe intervention that prevents human cancer.
Blind mole rats use yet another strategy. When their cells overproliferate, repetitive genetic elements become active and unusual nucleic acid molecules accumulate in the cytoplasm. A danger sensor called J-sting then triggers interferon signaling and collective cell death. Components of this alarm also exist in mice and humans. Activating them therapeutically is difficult. The same inflammatory machinery can damage healthy tissue if it fires too broadly or for too long.
A bowhead whale can exceed 200 years and carry tens of tons of living tissue. A 2025 study found that its cells repaired DNA double-strand breaks more accurately. They also accumulated fewer mutations than comparison cells. High levels of a cold-responsive protein called CIRBP improved repair. This occurred in laboratory systems, including human cells. That suggests prevention by faithful repair rather than automatically killing every damaged cell.
The sharks develop both benign and malignant tumors. Shark cartilage was never a logical cancer cure, and it failed the evidential test. Hydra, tiny freshwater animals famous for regeneration, can also develop spontaneous tumors in laboratory and wild-derived strains. Cancer, like cheating, is deeply connected to multicellular life rather than being a uniquely human design flaw. Nature supplies resistance mechanisms, not magical exemptions. Comparative oncology works as a discovery pipeline rather than a pet shop pharmacy. First, identify a reliable species difference and establish its mechanism. Reproduce it in cells, then test a controllable version in animals. Finally, evaluate safety and benefit in people. Naked mole rat HAS2 has reached the engineered mouse stage. Bowhead CIRBP has influenced human cells in a laboratory. Neither result authorizes a human supplement, gene edit, or treatment today. Carcinomas arise from epithelial tissues, such as skin, bowel lining, and glandular organs. Sarcomas arise from bone, muscle, or other supporting tissues. Leukemias begin in blood-forming tissue and usually do not make one solid mass. Lymphomas arise from lymphocytes, and brain tumors form another biologically varied set. These families differ in how they spread, how they are sampled, and which treatments can reach them.
A breast tumor may depend on estrogen signaling, overproduce HR2, express both features, or have neither. A hormone receptor-positive tumor may be vulnerable to endocrine therapy. A HER2-positive tumor may respond to antibodies aimed at that receptor. Triple-negative breast cancer lacks those particular handles and requires a different strategy. The organ name tells us where the investigation starts, not where it ends.
To metastasize, a cell must detach, invade, and enter blood or lymph. It must survive transport, exit into another tissue, and establish a functioning colony. Most traveling cancer cells failed somewhere in that sequence. The successful minority must adapt to a foreign environment and recruit local support. Metastasis is an improbable cascade repeated across an enormous cell population. It is not a cell casually catching the next bus.
If breast cancer cells establish a tumor in the lung, it remains metastatic breast cancer. It is not lung cancer. A pathologist can recognize the cellular origin and use markers to confirm it. Treatment follows the tumor's origin and molecular features. Those cells retain much of the breast cancer's biological identity. The address changed, but the disease did not acquire a new passport.
Spread often makes cure harder because surgery or one radiation field cannot reach every site. Yet metastatic is not a universal synonym for incurable. Germ cell tumors of the testes can remain highly responsive to cisplatin-based chemotherapy even after dissemination. Stage matters enormously, but cancer type and treatment sensitivity determine what that stage means.
Imagine that screening reveals a small breast abnormality in a person who feels completely well. The image shows location, shape, and density, but it cannot by itself prove malignancy. Further imaging may refine the target and guide a needle biopsy. The clinical question is still, what is this tissue? It is not which internet remedy should be tried.
A biopsy preserves cells and often their arrangement within tissue. The pathologist asks whether normal boundaries are breached. They also identify the cell lineage and assess the abnormal architecture. Special stains can reveal proteins that narrow the diagnosis. One small tissue cylinder can clarify a vague radiological shadow. It can reveal an invasive carcinoma with a defined origin.
Grade describes how abnormal the cells and tissue look and can indicate likely aggressiveness. Stage describes extent, including tumor size, local invasion, lymph nodes, and distant spread according to a cancer-specific system. A small high-grade tumor and a large low-grade tumor are not the same problem. Mixing grade with stage removes information precisely when clarity matters most.
The breast biopsy can be tested for estrogen receptors, progesterone receptors, and HER2. Too much HER2 protein or amplification of its gene identifies a growth pathway that certain drugs can target. A positive result therefore changes treatment options rather than merely decorating a report. If the marker is absent, a HER2-directed drug may offer little benefit and still carry risk.
A biomarker can be prognostic, predictive, diagnostic, or useful for monitoring, and those jobs are not interchangeable. One marker may predict response only in a particular cancer and treatment setting. The same tumor can contain cells with different marker levels, and markers can change after treatment or recurrence. Precision oncology narrows uncertainty, it does not abolish biology.
Some tests search blood for tumor-derived DNA fragments. In selected settings, they can help identify mutations, monitor response, or detect molecular evidence that deserves investigation. A negative result does not prove that no cancer exists. A small tumor may release too little material for the assay. A promising technology becomes clinically useful only after its exact question and limits are validated.
A treatment planning starts by asking what success should mean in this case. The aim might be cure, reducing a tumor before surgery, preventing recurrence, controlling advanced disease, or relieving symptoms. The same medicine can serve different goals in different sequences. Without the goal, a list of treatments is pharmacological wallpaper.
For a localized colon cancer, surgery may remove the affected bowel segment, nearby tissue, and regional lymph nodes. The margin shows whether tumor reaches the cut edge. Lymph nodes help reveal whether cells traveled beyond the primary site. Surgery can cure disease that is genuinely confined and completely removed. It cannot reliably remove invisible cells already dispersed throughout the body.
And radiotherapy deposits ionizing energy into a carefully planned volume. It damages DNA more severely in the target than in surrounding tissue. Fractionating the dose across sessions allows normal tissues time to repair, while repeated damage accumulates in the tumor. Geometry, motion, and organ tolerance shape the plan. Calling it simply radiation misses the extraordinary spatial engineering involved.
cisplatin forms damaging links in DNA, and germ cell tumors are unusually poor at surviving that injury. Combined with medicines such as etoposide and bleomycin, it transformed metastatic testicular cancer. A frequently fatal disease became one that is often curable. Outcomes still differ between good, intermediate, and poor-risk metastatic groups. The example proves that spread does not erase curability when the disease retains an exploitable vulnerability.
Historical international risk groups reported 92% 5-year survival for good-risk metastatic testicular cancer. They reported 48% for poor-risk disease. Later pooled treatment data improved those figures to about 94% and 71% respectively. These are group estimates from particular eras, definitions and treatments, not guarantees. Their value is to show both remarkable chemosensitivity and the persistent importance of biological risk.
HER2-positive breast cancer was once recognized as an especially aggressive subtype. Researchers found that excess HER2 signaling was not merely a label but a growth driver. Trastuzumab, an antibody designed to bind that receptor, improved outcomes when added to appropriate treatment. A bad prognostic feature became a therapeutic handle because mechanism connected diagnosis to intervention.
Trastuzumab binds HER2 on the cancer cell's surface and interferes with signaling. It can also recruit immune mechanisms against strongly expressing cells. It is used only where testing supports that target and usually as part of a larger regimen. Some tumors fail to respond and others evolve resistance through alternative signals or changes around the pathway. Targeted does not mean harmless, perfect, or permanent.
Many breast cancers use estrogen receptor signaling, while many prostate cancers use androgen receptor signaling. Endocrine treatments can reduce the hormone, block its receptor, or prevent its production. This may control growth without directly poisoning every dividing cell. Resistance still develops when the cancer activates the receptor differently or finds another survival route.
T cells carry inhibitory checkpoints that restrain immune damage to normal tissue. Some cancers exploit those checkpoints to quiet an attack. Checkpoint inhibitors block selected inhibitory signals and can produce durable responses in a subset of patients. They can also unleash serious inflammation in healthy organs. Removing an immune brake is not the same as simply strengthening immunity.
A treatment sequence may shrink a tumor, remove it, and then attack microscopic disease left behind. Combining mechanisms can reduce the chance that one pre-existing resistant clone survives everything. Yet combinations also combine toxicities, and more treatment is not automatically better treatment. Trials must show that an added intervention improves an outcome worth the additional harm. Anti-cancer care also includes controlling pain, nausea, infection, fatigue, nutrition problems, and psychological distress. Palliative care can begin alongside treatment intended to cure or control disease. It focuses on symptoms, communication, and quality of life rather than on surrender. A biologically clever therapy is not successful if the person cannot safely receive or tolerate it.
A scan has a resolution limit, and a laboratory assay has a detection limit. A tumor can disappear from available tests, while a small population of malignant cells remains. In blood cancers, measurable residual disease describes cancer detected by sensitive methods below what ordinary examination can see. Undetectable means below this test threshold, not metaphysically proven absent. A resistant cell may change or amplify the drug target. It may activate a bypass pathway or prevent enough drug from reaching that target. Other cells may repair the damage, enter a slow state, or receive protection from surrounding tissue. Chronic myeloid leukemia and HER2-positive breast cancer provide concrete examples of target alteration and pathway escape. The phrase treatment resistance hides several different engineering problems.
Recurrence can appear at the original site, in regional nodes, or at a distant organ. It may come from residual cells that survived because of location, dormancy, or biological resistance. Recurrence does not show that the first treatment was pointless or that anyone failed. Earlier therapy may still have removed sensitive disease, prolonged life, or produced years without detectable cancer.
Cure means the cancer has gone and will not return, but medicine cannot prove the second half immediately. Complete remission means signs of cancer have disappeared on the assessments being used. A long, complete remission may eventually give clinicians strong confidence that cure has occurred. There is no universal 5-year stopwatch that converts every cancer into the same certainty. Relative survival compares people with a cancer against similar people in the wider population. It describes groups diagnosed in a particular place and era. The newest treatments often have not yet had long follow-up. It cannot incorporate every detail of one person's tumor, health, and care. A statistic is evidence for a clinical conversation, not a verdict delivered by arithmetic.
Earlier detection can find some cancers before extensive spread, when local treatment is more likely to succeed. Screening can find indolent disease that would never have caused harm. It can also produce false alarms or miss aggressive disease between tests. That is why evidence supports particular screening tests for particular populations rather than scanning everyone for everything. Personal decisions depend on age, risk, and local guidance. Tobacco smoke exposes tissue to a mixture of carcinogens rather than one mysterious toxin. Avoiding tobacco or stopping use reduces the probability of several cancers. Past exposure does not make a future diagnosis inevitable. Prevention works by shifting risk across a population, not by issuing immunity certificates. It remains one of the most powerful anti-cancer strategies humans already possess.
Human papillomavirus vaccination prevents new infection with high-risk viral types. It therefore prevents many cervical and other HPV-associated cancers. Hepatitis B vaccination reduces a major route to liver cancer. Treating selected Helicobacter pylori infection can reduce stomach cancer risk. These interventions prevent upstream causes rather than waiting to attack a fully evolved tumor. They show that effective cancer tools include vaccines and antibiotics. Oncology drugs are not our only tools.
So is cancer actually curable? There is no single cure for every disease called cancer. Many particular cancers are already curable, including some that have spread. Others can be controlled or placed into long remission. Animals may teach us new prevention strategies. Elephant genes, mole rat hyaluronan, and whale repair proteins remain research leads, not human treatments. The useful answer begins by naming the exact cancer and its extent. It also requires its molecular vulnerabilities and the evidence for that specific case.